Okay, this is section 3.4 from the PowerPoint slides. This is about, yes, here we go. Okay. Section 3.4, motion in two dimensions. Basically, we've got displacement and acceleration, and we're going to be taking into account both of those. And so you can have a change in velocity in either the X or Y direction, but now all of those things are going to have X and Y components. And so we need to take into account those two things. Generally, the displacement is going to point in the same direction as the velocity. Okay, so if we're considering each one of these little sections here, then displacement will point in the same direction as the velocity. Okay, and so we can break these down into little points in two-dimensional motion and object displacement, velocity and acceleration vectors all change. Okay, so it could be changing direction. Maybe the magnitude is changing, either one. All right. In both of those cases, it is the change in displacement divided by time. Okay, that's still the same definition of velocity, but now we have the X and Y components. And so we need to find the magnitude, okay? And so we'll divide the magnitude by the change in time. That will give us the velocity, okay? So we need to use the Pythagorean theorem on the X and Y component of the velocity. And I'm trying to go through this a little bit quicker because some of these videos are taking a long time. I think I'm saying important stuff, but you need to do the homework. And so hopefully I want to make these helpful and not uh too long. I get it. All right, let's look at this. It says estimate the kayaker's velocity during the time interval from 0.5 to 0.6. Okay, kayaker flies off a cliff. He's a brave man. Okay, so here we go. I am going to zoom in on here. Okay, so he's going to fly off the cliff here, and we want to know what is his displacement between 5 and 6. Okay, so I'm going to get out my little arrows here, and we're going to draw this. We're going to draw lines over here. And I'm going to go from here over to there, okay, because I want to know what's my Y displacement during this time and what's my X displacement. Okay, so I'm zooming in over here, and I guess this is 0.6 meters, maybe 0.5 meters. The book says it's 0.6. I guess it's 0.6. All right. And then this one is from about halfway over to here. Okay, so now I have my times here. Okay. Um, that's about half a meter, and this is 0.6 meters. You know what? Let's draw a little arrow, and we will compare, and we'll see, because I don't know if I believe that the Y one is okay. So I'm gonna draw an arrow. Okay. Yeah, that's that's about half a meter, right? Okay, and then no, that's not what I wanted. No. Just want to move it. No, it doesn't want to be moved. Not cooperating. You know what? It doesn't matter. Okay, I don't care. Yeah, we're gonna say this is 0.6, maybe 0.5. Yeah, it's hard to say from the graph, but it is a little bit 0.6. Okay, so that means our two displacement vectors, right? And I'll just be honest, here's what I got when I did this problem the first time. When I measured it, I said the kayaker moves down by 0.5 and he goes over an X by 0.6. The book says this is 0.6. I don't know if he can be that precise if you're just looking at it and you don't zoom way in. I'm gonna go with point 0.5. That's my velocity. Okay. I don't care what the book says. I'm right. So up here we have our displacements. Okay. And what we're doing here, this is D, and I'm gonna take my X component. So this is, yes. What am I gonna call my, yes, my component? Hmm. Yeah, we'll call the vector C. Okay, that's his total. That's his total displacement here. I'm just gonna call it C because I can't think of anything better. All right, I don't know why I picked C. All right, so here's C of X. Probably because I didn't want to pick Y. And this is squared, and this is CY, and that's also squared. Okay, so that's point 0.5 here, point 0.5 here squared. So uh this is Y, this is my X here. Okay. So this one's point 0.5, this one's point 0.5. Then I put that into my Pythagorean theorem. Okay, I get point 0.5 squared plus point 0.5 squared. That gives me 0.7071 meters. I divide by the time, and I get a velocity of 7 meters per second. I think that's pretty good. Um, in the book here, yeah, in the book, okay, they estimate that his displacement was zero point 0.8 meters. I have philosophical problems with that. The direction really doesn't matter. They didn't ask us for the direction, okay, but they just put it anyways. But we did the right thing, okay? Maybe our estimates were a little bit off, but our method is sound. Even if, I mean, it's hard to say there. I don't know how the heck you're supposed to get that.